Okay, this is Stats for the Behavioral Sciences, Chapter 10. We're going to start working on hypothesis testing using the binomial distribution. So if you recall, in the last chapter, we had an example in which we evaluated the probability that a friend of ours would correctly identify Starbucks coffee 6 times in a row in a blind taste test. We set a hypothesis in that example which enabled us to evaluate this probability. And that hypothesis was that our friend was guessing. So in a binomial example, or to make this a binomial experiment, we set P, the probability of a single guess correct, to be 0.5. And the reason to do that is because that represents a guess. If our friend was truly guessing, then it would be a coin flip. His or her ability to get the coffee correct would just be akin to flipping a coin. So then we used that fact to enable us to actually obtain a probability out of 6 trials of getting 6 correct answers, given that the probability of a correct answer would be 0.5. We ended up finding out that the probability of getting that 6 out of 6 was roughly 0.01, or we'd expect that to happen 1 in 100 times if we did this experiment over and over and over again. The key to that last example is we set our hypothesis before the experiment. And the reason that we have to do that is because that enables us to derive a probability distribution for our results. That is, that without setting that hypothesis, that P equals 0.5, that the probability of a success on any observation or trial was 0.5. If we had not set that, we would not be able to evaluate the probability of our friend's performance. So that's called deriving a probability distribution for our results. Our hypothesis represented nothing special, i.e. guessing, right? And so we began the experiment with skepticism. This is exactly how null hypothesis significance testing works. And this is the type of statistical inference for experiments that we're going to learn about. There are other ways to come to inferences in using statistics in experimental results. This is just one, and we're going to see that it's relatively easy to use in terms of keeping calculations simple. But the logic of it is a little bit awkward. And so we're going to work our way through an example using data. So in this chapter, we're going to use what's called a repeated measures design or a repeated measures experiment. This is an experiment in which we have a set of people as our participants, and we measure something about them more than once. In this particular repeated measures experiment, there are going to be 2 measurements, or each person is going to have a pair of measurements on the same variable. Okay, so our experiment is going to be revolved around the question of whether marijuana, or more specifically THC, can help someone who is suffering from AIDS want to eat more. So does marijuana help AIDS patients' appetites? This example is in the book, so you can look to it. I'm not going to read the whole thing, but the gist of it is that we randomly sample 10 AIDS patients from a hospital, and this hospital has a very large population of AIDS patients being treated on an outpatient basis. None of the patients have taken marijuana before, and so that's important. We'll discuss why that's important. And then we do a number of things to make sure that there's no other bias. Half of the people, we give them marijuana first, and then measure their appetite, and then give them a placebo and measure their appetite. The other half, we switch it. The important things right now is that there are going to be 2 measurements for each person. One measurement of appetite on the day in which they've ingested THC, and another measurement of appetite on the day in which they've ingested a placebo pill that they think might have THC. So this is going to happen on day 3 and day 6, and half of the patients will get THC first, and half of the patients will get the other stuff first. So the real design, like I said, is that we want to examine the effect of THC versus placebo in 10 people. And we do that by examining their food intake after placebo and after marijuana or THC. So each person's food intake is measured under 2 conditions, a placebo condition and a THC condition. Ask yourself, why do we do this switching around? This is called counterbalancing, which is that half of the participants receive the treatments in one order and half of the participants receive it in another order. Ask yourself why you think that might be important. The reason that we do something like that is, again, in any experiment, we would like each person's results to be independent of the others, and we would also like to reduce the influence of any confounding variables. So the confounding variable in a repeated measures design is the order in which they receive the treatments. Right? You might imagine that even if a person is unaware of whether they're taking placebo or taking a drug at any time, that having done one first may affect their experience of the other one. That's called an order effect. So we try to reduce that in repeated measures experiments by giving a different order to each participant, or in this case, since there's only 2 possible orders, to randomize who gets which order. So essentially that means that half of the 10 people in our experiment will take THC first on day 3, and we measure their appetite. Then they take placebo on day 6. They don't know which is which. And the other half, we switch it. They take placebo first, then THC. Again, we call this repeated measures because the same set of participants are in each condition. And very importantly, what we measure under each condition is the same dependent variable. That's very critical to the next step. So in each measurement is appetite. The only thing that changes is the conditions under which we measure their appetite. So let's have a look at the data. The data for this experiment looks just like this. What we've measured for all 10 patients, in the first column you see the amount of calories they ate in the 24 hours after taking a pill with THC in it, the experimental condition. Now remember, they don't know which is which. They're just taking 2 pills, 1 placebo, 1 THC, but they don't know which is which. So patients 1 through 10 we see in the experimental condition column. This is their food intake in calories after eating THC on either day 3 or day 6. The third column is how much they ate after they took a placebo pill. Now, if you look at each row in the table, we'll see that, for example, patient number 1, that person ate 1,325, so 1,325 calories after ingesting THC. They ate only 1,012 calories after placebo. So what we want to calculate is a difference. How much more did they eat after ingesting THC in the experimental condition versus control? And you see that in the 4th column. When we see a plus next to it, which in this experiment is going to mean a plus, means they ate more after THC. So they ate more in the experimental condition. And this person ate 313 more calories in the experimental condition. If we look down that difference score column, we see the difference in calorie intake for the rest of the 9 people. And if you look, you'll see that everyone has a plus except for person number 7. Person number 7 just so happened to eat 36 fewer calories in the experimental condition versus control. So there are several options for statistical analysis of this data set. What we're going to do, though, is we're only going to pay attention to the sign of the difference. So we're only going to pay attention to whether someone has a plus in front of their difference score or a minus in front of their difference score. The reason for that is because we can turn this into a binomial probability problem by considering the fact that each person's difference could either be a plus or a minus. So that's two options, binomial. And that allows us to obtain a probability of the result that we have, which is 9 out of 10 pluses. But before we do that, we're going to develop a little bit more of the logic of what we're about to do. In null hypothesis significance testing, we make a distinction between two statements about the effect of our variable, our treatment variable, which in this case is the thing that's different in the conditions, whether or not there was THC in the pill. So we start, and this can go either way, but for our book, in our procedure, we're going to start by stating what's called the alternative hypothesis. The alternative hypothesis makes the claim that the independent variable has some effect on the dependent variable. And remember, the independent variable is the condition, is the set of conditions that's manipulated by the experimenter. So in this case, our independent variable is the presence of marijuana or THC, and the effect that we think it might have is that it increases appetite in AIDS patients. So the alternative hypothesis always makes a statement that usually represents what our hunch is about the effect of the independent variable. The second type of hypothesis is essentially a negation of that statement. This is a hypothesis called the null hypothesis, and that's where the null in null hypothesis significance testing comes from. This is a hypothesis that makes the claim that there's no discernible effect of the independent variable on the dependent variable. So in our case, we would state the null hypothesis being that marijuana has no effect on appetite in AIDS patients, or it may even decrease the appetite. Now, these two hypotheses are what we call directional hypotheses because they actually make a statement about the direction of the effect. So the alternative hypothesis says that marijuana should increase appetite. So it doesn't just say that it should affect appetite, it says it should increase. Later on, we're going to introduce what we call non-directional hypotheses, but we're going to stay with directional because they're the simplest and continue to motivate. So this is always the first step in our hypothesis testing situation, is we need to state what these two hypotheses are. What's the alternative hypothesis and what is the null hypothesis? The other thing is that in the hypothesis statement, we're also identifying a population of interest. So the population of interest here is AIDS patients. We make that statement clear in the hypothesis because the effect has to be generalizable to some population, and so we make sure that we state that in both hypotheses, that marijuana increases appetite in AIDS patients or it does not. That's very important, and we'll see that later. So how does probability, we've learned all this stuff about probability, how are we going to make use of it? Well, the way we make use of it is through what we call a decision rule, and that means that we use a probability value for our results. We literally calculate the probability of obtaining our particular results, and we use that probability to make a decision about whether or not we can reject one of our hypotheses. In null hypothesis significance testing, we use the Greek letter alpha to represent our decision rule. And alpha itself is actually a probability value as well. It's a value that we decide on a priori before we collect the data. And what it represents is it's a place, it's a threshold. It's a value where we would change our decision from not rejecting the null hypothesis to rejecting it. So alpha is actually a probability, and that makes our decision rule. The decision about a null hypothesis and null hypothesis significance testing is based on comparing the probability of our experimental results under the assumption that the null hypothesis is true. We compare that with alpha. Now, just a note, alpha itself is not the probability that the null hypothesis is true or false. It's also not the probability that our result occurred by chance. It's a little bit different. What it actually is it's a probability that if we obtained it in our experiment, we're right on the line of being able to decide that we should reject the null hypothesis. So literally, it's a threshold. A lot of people who are learning this for the first time then get confused. So like, how do we know what alpha is? Well, alpha, we get to pick it. So we get to decide what alpha is. And often we set alpha to be either 0.05 or 0.01. Now, there are principled ways to pick alpha. By convention, we're going to use one of these two. Generally, we're going to use 0.05. And then we make a decision about the null hypothesis by comparing the probability of our results, which we need to compute based on our data, with alpha. If our obtained probability is less than or equal to alpha, we reject the null hypothesis. If you recall, in our Starbucks experiment, we obtained a probability of 0.01 that our friend would get 6 out of 6 if he was truly guessing. If we had set alpha to be 0.05 in that experiment, our obtained probability, 0.01, is less than alpha. So in that case, we could reject the null hypothesis that our friend was actually guessing. If, however, it turned out that the probability of 6 out of 6 was something like 0.10 or 0.2, that obtained probability is greater than alpha, and in that case, we say that we fail to reject the null hypothesis. So in every null hypothesis significance testing situation, we choose what alpha is at the beginning. It's a threshold. Then we run our experiment, we collect our data, and we use one of many procedures to evaluate the probability of our experimental results if the null hypothesis is true. We compare that to alpha, and if our probability that we obtain from our results is less than or equal to alpha, we can reject the null hypothesis. If our probability is greater than alpha, we say that we fail to reject it or that the experiment is inconclusive. Now, very importantly, if you note, even though we've set an alternative hypothesis, the whole procedure is really about deciding whether or not to reject the null hypothesis only. So in fact, we're really only testing the null hypothesis directly. And the reason for that is because it makes our probability calculation easier. So by setting a null hypothesis, what we're essentially doing is we're enabling ourselves to compute the probability of our results given that that null hypothesis is true. The term statistical significance is synonymous with rejecting a null hypothesis. So when we make a reject decision, that usually results in the statement, we have a statistically significant effect at the alpha level of whatever it was, 0.05, 0.01. We can also say these results are reliable at that level. When we fail to reject the null hypothesis, we make the statement that the results were not statistically significant, but we don't say they're insignificant. It's just that they weren't statistically significant. We'll get to more on that later. The terminology gets a little bit tough here. We have to be very careful, and we'll talk about the errors that we can make in a little bit. Two important points that we should make right now. So statistical significance doesn't always equal practical significance. So what does that mean? Just because an experiment finds a significant result doesn't mean that we have a large effect. It doesn't mean that what we've actually found is interesting. The same thing, well, not the same, but on a related point, if we fail to reject the null hypothesis, it does not mean that the null hypothesis is in fact true. We just do not have enough confidence or really enough evidence to make the statement that it's false. So these are very subtle parts of null hypothesis significance testing that students tend to get wrong, even professionals get wrong. And again, it's unfortunate that we have to be this subtle, but the upshot of this procedure is that the mathematical part is made much simpler than it could be. Okay, so let's just summarize for a minute. We've talked about the alternative and the null hypothesis, statements about the effect of our independent variable or lack of the effect. And we talked about alpha, our decision rule. And we've stated that what our goal is to make a decision about our data using alpha. So we can reject the null hypothesis, which means that we have a statistically significant effect, if the probability of our experimental results under the assumption the null hypothesis is true, if that probability is low, less than alpha. We can reject the null hypothesis, we have statistical significance. The opposite is true. If the probability of our results under the null hypothesis is not very low, is not less than alpha, we can't reject it and we have a non-significant or not statistically significant result. So let's put this to use now with the sign test. In the real world, we would usually evaluate repeated measures data of the type in our marijuana experiment with a t-test. But we're going to use the sign test. It's a little simpler, and it allows us to focus on how we're using probability to evaluate our experimental results. So the sign test is essentially making use of binomial aspects of the experiment. So the way that we turn our marijuana experiment into a binomial experiment is we say, well, the null hypothesis represents the fact that each person could either increase or decrease food intake at random if marijuana had no effect, right? If there was no effect of THC or marijuana on appetite in our participants, it would be totally random. It would be a coin flip whether or not they ate more or less under each condition. Right, so we make that statement that seems logically a good way to represent a null effect. And so in binomial land, the way we do that is we say, well, we should pick a binomial distribution with a probability of success of 0.5, right, which describes the probability that any one person would have an increase in appetite, right, that it's a coin flip. In our particular experiment, we have 10 people. Each person is going to do something twice, but our observation is really about, did they go up or did they go down? And so in that case, if we assume that no one stays the same, that everyone must change, they must go up or they must go down, each person ends up being a trial. And our observation could be that they go up, it could be that they go down. So this makes a very nice binomial distribution problem. We're going to call the P events, or X, right, the pluses, right? So in this case, we're going to be interested in increases in food intake, or an increase or a positive difference score representing that they ate more after THC than placebo. So if we take a look at our data again, we see again that 9 of the 10 people go up. So we have 9 P events, X equals 9. And so what we need to do now is use the binomial distribution where N equals 10, P equals 0.5. And let's start by just evaluating the probability of our particular result. Let's evaluate the probability of 9 out of 10 successes, exactly 9 with P equals 0.5. So in Excel, we can do that with binom dist range. Note I'm only typing in 3 numbers. In this case, I'm only interested in N equals 10, P equals 0.5, and just that experimental result of 9 pluses. And I find that that probability is 0.0097, or we can round up to 0.0098. Now, if we had used alpha 0.05, right, this is the probability of our experimental result under the null hypothesis assumption, right? The null hypothesis assumption is that the treatment doesn't work. So each person goes up or down as a coin flip. Probability of success on each trial is 0.5. In that world, we computed that the probability of 9 successes out of 10, 9 pluses out of 10, is much less than our alpha criterion, 0.05, right? The probability of our result is 0.0098. So if this was our experimental result, we would reject the null hypothesis that marijuana does not affect appetite, and we would go with the alternative hypothesis, which is that marijuana increases, right? So that's the only mathematical component of the sign test, is simply turning the problem into a binomial distribution and then calculating probabilities. However, we've done some incomplete work here, so we're going to come back to this. So we've now seen a little bit about null and alternative hypotheses and how to use the decision rule. Let's talk a little bit about alpha for a minute, and about the fact that this procedure, this null hypothesis significance testing procedure, is not a perfect procedure. Even though in our experiment just now, we saw that 9 out of 10 people ate more, that could have been a fluke, right? It could have been that we just, by accident, picked 9 people who really, really like THC, and then they get the munchies. But does that mean that everyone that we give this medicine to that's an AIDS patient will go up? Well, that question basically has to do with whether or not our decision from our experiment is correct or incorrect. Alpha is actually connected to one type of error that we can make that we call a type 1 error. It's not a very creative name. Type 1 error is when we make a decision to reject the null hypothesis, and that's wrong, right? So in fact, our data suggests we should reject the null hypothesis, but in fact that would be an error, that this is a fluke, that this is really a false positive. So in any null hypothesis significance testing situation, there's a probability that we've made an error when we decide to reject the null hypothesis. When we set alpha, what essentially we're doing, so when we pick, for example, alpha of 0.05, we're setting an upper limit on the probability that our decision might actually be a type 1 error. So when we set alpha of 0.05 as our decision criteria, that means that in the long run, if we were to do this experiment over and over and over again, 5% of the time, when it came up as a reject decision, that actually would be wrong, right? And this is essentially akin to, in medical diagnostic testing, type 1 error is a false positive. So the false positive rate in a medical diagnostic test is akin to the type 1 error rate in an experiment. And we try to keep this low, right? We want to avoid false positives because that makes us think that something works when in fact it doesn't, right? Especially if we're looking at interventions like giving someone a treatment for appetite or something like that. So type 1 error is very important. It is always lurking in any null hypothesis significance testing situation. And this is the reason why, if we get a significant result, we have not proved anything. All we've done is we said, well, our data at this point are inconsistent with the null hypothesis. However, we may have made an error. We set up the experiment such that that error, hopefully, the error rate is quite low, but we're never really sure. So that's upsetting to some people in statistics, and it is a downside of this procedure, that we always have to be aware that when using this procedure, our decisions that we make about the null, they could be incorrect. All right, so let's actually put this to use a little bit further in our experiment. So we actually have to do a little bit more to get at type 1 and 2 error with our experimental results. And so we were actually incomplete when we evaluated our experiment. We only looked at the possibility or the probability of 9 out of 10 pluses on the dot. In fact, in null hypothesis significance testing, we have to actually evaluate some of the other outcomes that may have convinced us. So for example, what if 8 out of 10 people increased appetite, or 10 out of 10, right? So what we actually have to do is to compute what we're going to call a p-value, which is also called a tail probability. And so this is actually what we need to compute in any experiment. And this actually is the reason why I had you use binomial dist range. So you're going to see that in a minute. So a p-value, very important. A p-value is our term for the probability of obtaining the experimental result I got, or one that is more extreme if the null hypothesis is true. This is what we need to compute in all of our experiments, and this is what we compare to alpha. So the 0.0098 that we already computed is missing some information. So let's take a look at what. In this picture, you're actually looking at a graph of the binomial distribution for n equals 10 and p is 0.5. Notice that it's symmetrical, that in fact the highest probability number of pluses if the null hypothesis is true is 5 out of 5, right? If the null hypothesis is true, then we would expect that 5 people go up and 5 people don't, that the experiment doesn't work. Note that our result is 9 out of 10, and 9 out of 10 is right here. And note, we already computed that the probability is 0.0098. But also note that there are more extreme results that we could have obtained, right? We could have actually obtained 10 out of 10, which would occur with a probability 1 in 1,000, 0.0010. So what we call a tail probability is the total probability of our results and everything that we could have gotten that was more extreme than that. So our calculation in this case should have been an addition rule, the probability of 9 out of 10 or the probability of 10 out of 10, which we already know how to do. So if we were doing it by hand, we would just add those two probabilities together and we would get 0.0108. Now note, this is now our actual p-value, our tail probability, in the direction of our effect. And by the way, 0.0108 is still less than our alpha level, so we can still make a decision to reject the null hypothesis. So we can reject the idea that THC does not do anything to appetite and go with the fact that it increases it. Now, what we've just done is done a tail probability in one tail, right? We looked up here. We ignored what was going on down here, and we just looked at the top tail. This sometimes is what we will do, but it's much more likely that we'll conduct what's called a two-tailed test. So our original hypothesis was directional, so we really only cared about increases. But what if we changed our hypothesis to a much more simple statement, which is that THC or marijuana simply just has no effect on appetite, and the alternative is that THC does change it in some way, we're not sure. Does it make it go up? Does it make it go down? This is what we call a non-directional test because we're not making a prediction here that we would expect a large number of people to go up or a large number of people to go down. We're just saying, well, we think something will happen such that it won't be a 50-50 split. In a non-directional test, our tail probability, our p-value, has to make use of both tails. Now, the easiest way to do that in a symmetrical distribution, in the case of what we have here, this is a perfectly symmetrical distribution. So notice that as we go down on this side, these numbers are equal to these numbers. It's a perfect reflection. So when we do this, when we evaluate the probability in both tails, essentially all we're doing is getting the one-tailed probability that we already have and multiplying it by 2. So let's take a look at that, right? A two-tailed p-value is the probability of our data, given the null hypothesis is true, using both tails. So it's the probability of getting our experimental result, if the null hypothesis is true, or a result that's more extreme, meaning further in either of the tails. So again, if we were computing this by hand, we could look up in a binomial trial the probability of 0 or 1 or 9 or 10 successes. If you just add those together, and we get 0.0216. Now notice what's happening here, right? 0.0010 plus 0.0098 plus 0.0098 plus 0.0010. Well, we already know what 0.0010 plus 0.0098 is, right? It's that 0.0108 that we already computed. This 0.0216, our two-tailed probability, is just 2 times that one-tailed probability. And that will always be the case when you have a symmetrical null hypothesis distribution, which is going to be true in this class with exception of when we get to analysis of variance. So when we're doing a two-tailed test with a sign test and a probability of 0.5, when we're learning about z-tests and t-tests, we're going to have symmetrical distributions. And so a two-tailed probability value is simply just 2 times the one-tailed probability value. Also note that our p-value, two-tailed p-value, is still less than alpha, so we can actually reject this null hypothesis with a two-tailed test as well. Okay, so the important component here is that we will want to, if you're asked for a two-tailed test, or you're comparing your result to a two-tailed alpha, what that means is you have to compute the one-tailed probability using Excel and then multiply it by 2. We're going to look at an example, but before we do that, I just want to kind of just sort of summarize this. So first of all, this is controversial, but most statisticians in the behavioral sciences suggest you should avoid one-tailed tests unless you have very strong theoretical reasons not to. Although some people say, forget about that. By default, we're going to use two-tailed or non-directional hypotheses in this course because they're very common. A non-directional null hypothesis is usually termed, we phrase it in terms of like no difference between treatment and experimental groups, or no difference among conditions, or no effect of the independent variable. And then for a non-directional alternative hypothesis, we'd say something like there's some difference between the treatment, or there's some effect of treatment. Right? We generally use two-tailed alphas of 0.05 or 0.01. This is changing. Some people are calling for 0.005, but we're going to stay with 0.05 or 0.01. This will always be given to you. Alpha will always be given to you. And if it's not, just assume that it's 0.05. Okay? All right. So in this chapter, we're trying to get used to the following logic. To evaluate any type of experimental results using this procedure, you must set up the null and alternative hypotheses and select alpha. You then use some procedure to evaluate the two-tailed probability associated with your experimental result. Now, in this chapter, we used the sign test, and the null hypothesis gave us that we can use a binomial distribution with some n and p equal to 0.5, and then our experimental results are evaluated on that distribution. In other chapters, we're going to learn different test procedures with different probability distributions. Importantly, once you've obtained your two-tailed alpha, you compare your two-tailed probability, your p-value, you compare that to alpha. If your p-value or your obtained probability is less than or equal to alpha, you reject the null hypothesis, you have a statistically significant result. If the obtained probability is greater than alpha, you fail to reject. Okay? So let's finish this up with a little practice. This is another sign test problem. This is problem 10.3 on page 264 of your book. So a corporation psychologist believes that exercise affects self-image. To investigate this possibility, 14 employees of the corporation are randomly selected to participate in a jogging program. Before the beginning of the program, they're given a questionnaire that measures self-image. Then they begin the jogging program. The program consists of jogging at moderately taxing rate for 20 minutes a day, 4 days a week. Each employee's self-image is measured again after 2 months on the program. We have results below, and the way we interpret these is in either the before or after jogging column. The higher the score means they have a higher self-image. A score of 20 means that you've got the highest possible self-image. Okay, so let's look at the data first, and then I want you to try to solve this problem. So pause the video and see if you can work your way through A, B, C, and D. But before you do that, let's just make a note. There's 14 people, okay? So to fit this all on one page, this is participant 1's before and after, participant 2's before and after, so on and so forth, okay? So what you're going to do is count a plus. So the first thing we've got to do is how many pluses are there, right, when we get to that part. Right, so how many P events, how many successes out of these 14 subjects, how many of them can we term a success? That's what we want to count up. So a success for this problem, or a plus, is someone that had a higher self-image after jogging. Okay, so higher self-image after jogging. So see if you can work your way through A, B, C, D, and see if you can get a one-tailed p-value, multiply it by 2 to get a two-tailed, make a decision, and then try D and E. And then, so pause it and try that, and then unpause it, and I'll go through the answers. Okay, so first things first, A asks us, what's the alternative hypothesis? Use a non-directional hypothesis. The alternative hypothesis is always saying something about that our independent variable, which is jogging, has some effect. And so what is it affecting? It's affecting our dependent variable self-image. Null hypothesis would be that jogging has no effect on self-image, right? Negates it. And note, this is non-directional because we're not saying jogging makes self-image go up or down. We're just saying it affects it. So a non-directional hypothesis has to be evaluated with a two-tailed probability. So here's how we do that. The first thing you got to do is set up the problem as a binomial problem. So since there's 14 people, n is 14. For the sign test, p, the probability of success, not our p-value, but p, the probability, the binomial parameter p, is 0.5. That's always true for a sign test. That represents, in this case, right, we should expect that if the null hypothesis is true, 7 people would show higher self-image after jogging, but the other 7 would not. Right? So if you're counting correctly, you should find that 12 of the 14 people had higher self-esteem after jogging. So given that 12 out of the 14 people this happened, first find the one-tailed p-value, then multiply it by 2 to get the two-tailed and compare it to alpha. Let's start with the one-tailed p-value. The one-tailed p-value turns out to be approximately 0.0065. Now, how did I get that? Here's where Excel comes in, right? I use binom dist range. Remember, the first number is number of trials, that's n. Second number is the p parameter of the binomial, that's 0.5 for our null hypothesis. And now our tail probability is a probability of at least 12 successes, right? So we put 12 in there all the way up to 14, and we return something we can round up to p, one-tailed p-value of 0.0065. Now we're not done. we need a two-tailed p-value because this is a non-directional hypothesis. So we simply take 0.0065 and multiply it by 2. And this is our actual two-tailed p-value. It's 0.0135. If we use two-tailed alpha of 0.05, clearly our p-value is less than alpha, and so we can reject our null hypothesis. Okay? Now D and E get back to the other. The answer to D rests on what your decision is. So what error might you be making if you make a reject decision? Well, the only error that you could make if your decision is to reject is a type 1 error. It could be that in fact jogging has no effect, that this is just a fluke. The last part, this is tricky. Some people might say that the population that this experiment applies to are employees at this corporation. One could make an argument that you could expand your inference that jogging, this type of jogging program might work for anyone that might eventually work at this corporation or any corporation like it. So the population argument is a little bit tricky, but it's always good to think about that. Okay, so go ahead and try your quiz, and we will spend some time on this. The important part is to understand the procedure of setting the hypotheses, evaluating the probability of your data, making a decision, and understanding the fact that there still could be a decision error in there.